This video is about Chapter 14 of the Business Statistics in Practice textbook, which is about simple linear regression. The simple linear regression model and the least squares point estimates requires a designed experiment. In a design experiment, we have the dependent variable, which is also known as the response variable, and this is the variable that we wish to understand or predict. And we also have the independent or the predictor variable, and this is the variable that we will use to understand or predict the dependent variable. And as mentioned before, we only have dependent and independent variables if we have a design experiment. If data was gathered through observations only, then there are no dependent and independent variables. Regression analysis is a statistical technique that uses observed data to relate the dependent variable to one or more independent variables. And the main objective is to build a regression model or a mathematical model that can describe, predict, and control the dependent variable based on the independent variables. And again, this requires data obtained through an experiment because regression analysis requires dependent and independent variables in the analysis. This is the form of the simple linear regression model. That's y equal to beta sub 0 plus beta sub 1 times x plus epsilon. And here are some notes about the regression model. Number 1, mu sub y is equal to beta sub 0 plus beta sub 1 times x plus epsilon. Mu sub y is the mean value of the dependent variable y when the value of the independent variable is x. So if x is equal to a particular value, this equation will always give us the average value for all possible values of y when x is equal to that certain value. Number 2, beta sub 0 is the y-intercept, the mean of y when x is equal to 0. So the linear regression model follows a slope-intercept form, and beta sub 0 is just the y-intercept of that line that we can construct using simple linear regression. 3, beta sub 1 is the slope. So this refers to the change in the mean of y per unit change in x. So as x changes, the corresponding change in the value of y is equal to beta sub 1. And finally, number 4, we have an error term denoted by the Greek letter epsilon, and this describes the effect on y of all factors other than x. Because for simple linear regression, we are only looking at two variables, the dependent and the independent variable. But in certain situations, there are other independent variables that can possibly influence the value of y, and those other possible factors that can affect the value of y are all integrated or encapsulated by this error term epsilon. Now here are the parameters of a regression model. As mentioned earlier, we have beta sub 0 and beta sub 1, and these are Greek letters denoting information derived from the entire population of x and y. However, in most regression analyses, we don't know the true values of these parameters because regression analysis is commonly performed based on a sample of information only. As such, we can use the data obtained from a sample to estimate the values of the regression parameters, and the estimates are the following. So b sub 0 is the estimate of beta sub 0, and b sub 1 is the estimate of b sub 1. So here is an illustration of the simple linear regression model. So this blue line here indicates the equation mu sub y equal to beta sub 0 plus beta sub 1 x. So using linear regression, we should be able to come up with an equation for that line. And the dots here represent the actual data we've gathered from your sample. And the slope again is the change in y per unit change in x. And then this is the y-intercept. So this is the value of y if x is equal to 0. So as you can see here, the dots, the actual points in the dataset, are not always on the line, and that is explained by the error term. So the line itself does not completely give us a perfect explanation to the value of y, because there might be other factors that affect the value, and those other factors are again combined into the error term. Now, since your data just comes from a sample, then you can only come up with a model based on the sample of information. And here are the estimates for your linear regression, and these are called the least squares point estimates. So for the equation of the line that we can construct, that is y hat equal to b sub 0 plus b sub 1 x, where y hat is the predicted value for y. X is your independent variable, and b sub 0 and b sub 1 are your regression estimates. Now, to compute for these values, these are the formulas. We have b sub 1 equal to ss sub xy over ss sub xx. And the values here are computed using these two formulas. So for ssxy, that's equal to this equation, or you can also compute for this using this equation. So any of these two will give you the same value. Now for ssxx, the formulas are these two, either this one or this one. So once you have ssxy and ssxx, then just get the ratio and you'll get the slope for the least squares line. Now, in order to get the value or the estimate for the y-intercept, we can use this formula. So that's b sub 0 equal to y bar minus b sub 1 times x bar, where y bar is computed using this formula, or y bar is simply the average of the values of y, while x bar is the average of all the values of x. So in order to compute for b sub 0, you need to have the value for b sub 1 first. So compute for this first before computing for b sub 0, and once you have these two values, then you can now construct your least squares line. In this example, we have the data set for the Tasty Sub Shop case. We have here the values for y and the values for x. Now, in order to come up with the least squares line, we need to solve for the following. So here is a column for the squares of the values of x. We have another column for the product of x and y. And here are their summations. So here is the summation for the values of y, the sum of the values for x, the sum of the squares of x, and the sum of the products of x and y. Now, from the last slide, we were able to get those summations, and once we have those values, then we can start computing for the values of b sub 0 and b sub 1 using those totals. So for ssxy, we just have to use the formula. So these values were determined earlier, so just plug into the second formula for ssxy and you'll get this value. For ssxx, again, just input the values we got earlier and you will get this value. And to get b sub 1, just get the ratio of ssxy and ssxx. And we will get an estimate for the slope, which is 15.596. Now, in order to compute for b sub 0, or the estimate for the y-intercept, we need to get the mean of y and the mean of x first. So we have the sum for y and the sum for x. So just divide that by the total number of measurements and we will get their respective averages. And then plugging in these values to the formula, we will get an estimate for the y-intercept of 183.31. So this is our estimate for the regression model. Y hat is equal to 183 plus 15.6 times the value of x, where x is the population, that's the independent variable, and y hat is the predicted revenue for the Tasty Sub Shop. And this line here, again, is the one characterized by this equation, and the dots here are the actual data points from the case. So again, as you can see here, not all the points are located on the line, but this is the best fit line. So this is the line that minimizes the distance of the actual points to the regression line. So if we use the equation to make a prediction for the value of x, so if you go back to the data set, there is one value of x which is equal to 20.8. So if you plug in the value of x to the formula, to the regression equation, we will get a prediction of 507.69. Now, this is the predicted value for y, but the actual data we obtained from the sample is a revenue of 527.1. So as we can see here, the actual value for y is different from the prediction for y, and the difference between the two is known as the residual. And the residual for this prediction is 19.41. Now, just like other statistical tests, the simple linear regression model has its assumptions, wherein the validity of the results of the regression analysis is based on the satisfaction of the assumptions of the use of the model, such that if the assumptions of the model are not present or are violated, then it means that the simple linear regression analysis or regression analysis in general might not produce accurate results, and the interpretations might not be valid for all the values of x and y, or all the values of the dependent and independent variables. So for simple linear regression, these are the assumptions. First is an assumption for the mean of the residuals, which is 0. Next, the constant variance assumption. Third, we have the normality assumption. And finally, we have the independence assumption. So here is an illustration of the assumptions. Again, the blue line here represents the regression model, and these are the values that can be constructed using the formulas that were discussed earlier. Now, here at this point, we have the mean yearly revenue when x is equal to 32.3. So for a particular value of x, which is 32.3, the point here on the line indicates the average. So it's possible that the actual value for y is not equal to the average, because again, there are multiple values for y. There can be different values of y, and sometimes it's lower, sometimes it's bigger than the average, but the assumption is that it follows a normal distribution. So the residuals follow a normal distribution, and the mean of the residual is at the point along the regression line. So that's also something that is shown here. So for this particular value of x, which is 61.7, the average value for y is equal to this point. And again, the possible values for y when x is equal to 61.7 follows a normal distribution with mean at this point, and then the values can be lower or higher than that point. Now, again, the model assumptions are are determined or are verified by looking at the residuals. So the residuals in the regression analysis are the main basis for validating the assumptions of the regression model. And as mentioned earlier, residuals, or denoted by small letter e, are defined as the difference between the observed value of y, so the actual value of y that you obtained from your sample, and the predicted value of y, which is denoted by y hat, using the regression model. So note that e is the point estimate of the Greek letter epsilon. So epsilon refers to the population parameter. So E is only the point estimate that we obtained from the sample. So if the regression assumptions are valid, then the population of potential error terms will be normally distributed with mean 0 and variance of sigma squared. And different error terms will be statistically independent. So that's what we mean by the independence assumption mentioned earlier. Now, in order to check if the assumptions are satisfied or not, there are multiple graphs and multiple tables that we can look at. So again, residuals should behave as if they are randomly independently selected from normal populations with mean 0 and variance sigma squared. And we are not really looking for minor deviations from the assumptions. So we can only say that the assumptions are violated if there are pronounced departures from the assumptions. So if the assumption is clearly violated, then as shown in the graphs in the tables later, then that's the only time when we can say that the assumptions are violated. But if the assumptions are approximately satisfied, so it's not pronouncedly different from the assumed assumptions, then the assumptions can be considered to be satisfied and we can proceed with the regression analysis. So in most actual data, assumptions will not hold exactly. So as long as the departures are mild, it will not affect our ability to make inferences for the entire population. So as long as the residuals approximately fit the model assumptions, and that will be good enough for us to make an interpretation. So here are some specific ways for us to verify those assumptions. For the constant variance assumption, in order to check the validity, we can examine multiple residual plots. So these residual plots are basically scatter plots with different values on the x-axis and the residuals on the y-axis. So one residual plot that we can look at is the plot of the residuals against the independent variable. So you have the independent variable on the x-axis and the residuals on the y-axis. We can also look at the residual plot against the predicted y value. So on the x-axis, you have the predicted values for y, and on the y-axis, you have the residuals. And if your data is time series data, the time can also be placed in the x-axis, and on the y-axis, you will have the residuals. So what we have to look for in the residual plots is the overall pattern of the plot. So if a pattern fans out, it means that the variance is increasing. If the pattern funnels in, then it says that the variance is decreasing. And ideally, we want to have a pattern that is evenly spread out, so it looks randomly dispersed along the x-axis for us to say that the assumption is satisfied. So here are illustrations of those cases. So here in this residual plot, we can see that the residuals are fanning out. So as this value changes, or as the value increases, we can see that the variation for the residuals are also increasing, and that is implied by the fanning out pattern. Now, if the residuals are funneling in, it means that as the value on the x-axis increases, the variation for the residuals are decreasing. And again, the constant variance assumption is satisfied if the residual plot relatively looks like this. So the residuals look like a horizontal band. The residuals are randomly dispersed, and they are not pronouncedly fluctuating as similar to the first two that we have seen. So as long as the residual plot looks horizontal and it looks randomly dispersed, then we can say that the constant variance assumption is satisfied. Now, another assumption is about the correct functional form. So the regression model used should be appropriate for the data. So you can see this, you can verify this in the scatter plot between x and y. So if there is a straight line or a linear relationship between x and y, then we can use the simple linear regression analysis. However, if the scatter plot shows a curved relationship, then instead of simple linear regression, then it's better to use a quadratic regression. So if the relationship between x and y is not linear, aside from the scatter plot, we can also see that in the residual plot. So the residual plot will also show us if the assumption for the correct functional form is violated. Now, for the normality assumption, we can check the histogram or the stem and leaf display of the residuals. And if the residuals look bell-shaped and symmetric, then we can say that the normality assumption is satisfied. Now, another way to check if the if the normality assumption is satisfied is through the normal plot of the residuals. So here it orders the residuals from smallest to largest, and if the normality assumption holds, the normal probability plot should have a straight line appearance. So this can be produced using different statistical software. So once the normal probability plot is produced, we just have to check if the graph looks like a straight line. If it's approximately a straight line, then we can say that the normality assumption is satisfied. Finally, for the independence assumption, again, the independence assumption says that the residual for a particular value of y and x should be independent from other residuals. Now, this independent assumption is normally satisfied, and this is only possibly violated when you have time series data. So if the data is not time series, then it can be reordered without affecting it. So in most cases, the independence assumption will be satisfied. But for time series data, the time-ordered error terms can be autocorrelated. So this is another concept which is exclusive for time series data only. So for positive autocorrelation, this refers to a positive error term that tends to be followed by another positive value, and negative autocorrelation happens when a positive error term tends to be followed by a negative value. So this can be seen by a cyclical error term over time. So you can see that the residuals follow a certain pattern. So here is an example of a plot that shows positive autocorrelation, while this one shows negative autocorrelation. So if these two can be observed, then we can say that the independence assumption is violated, and we can't rely on the linear regression analysis in order to make statistical inferences. A useful test that can help us determine the presence of autocorrelation in the dataset or in the residuals is through the Durbin-Watson test. So in the Durbin-Watson test, we compute for this value, small letter d, and this will be the basis of our interpretation for the presence of positive or negative autocorrelation in the residuals. So this is the formula for D, and this is automatically computed using different statistical software. In the Durbin-Watson test, there are two kinds of tests that we can perform. First is a test for positive autocorrelation, and the second one is a test for negative autocorrelation. For the first test, where we test if the residuals are positively autocorrelated, these are the hypotheses. So the null hypothesis states that the residuals are not autocorrelated, and the alternative hypothesis states that the residuals are positively autocorrelated. Now, to perform this test, we need the value of D, which is computed using the formula shown earlier, and then we will compare this to two values so that we can make an interpretation. The values are D sub L alpha and D sub U alpha, and these are values or critical values that we can obtain from the Durbin-Watson table. It's in the appendix of the Business Statistics Practice textbook. These values can be determined based on two values. We need k, the number of independent variables, and we also need n, the number of observations in the dataset. Furthermore, you also need the value of alpha to determine the value for the DL alpha and DU alpha, which should be compared to the test statistic D. Now, if the D is less than the lower value, that's DL alpha, then we reject the null hypothesis, which means that the residuals are positively autocorrelated. But if D is greater than the upper critical value, then we do not reject the null hypothesis, or the residuals are not autocorrelated. However, if D is in between those two critical values, then the test is inconclusive, meaning we cannot say if the residuals are autocorrelated or not autocorrelated. Now for the second test, we test the residuals for negative autocorrelation. And here, instead of comparing D to the lower and the upper limits, we will compare 4 minus D. So it's almost similar to the first one. If 4 minus D is lower than the lower limit, then we reject the null hypothesis, or we can say that the residuals are negatively autocorrelated. But if 4 minus D is greater than the upper limit, then we do not reject the null hypothesis, which means that the residuals are not negatively autocorrelated. Finally, if 4 minus D is in between the two critical values, then again the test is inconclusive, meaning we cannot tell if the residuals are negatively autocorrelated or not. The third test is a combination of the two. So we can perform a test for positive and negative autocorrelation at the same time by looking at D and 4 minus D. In fact, we have to perform both tests in order to perform this specific test. Here we perform both tests for positive and negative autocorrelation, and then the interpretation will depend on the results of those two tests. First, if either test says to reject the null hypothesis, then that should be the correct interpretation. For example, if we perform the first test and we were able to conclude that there is positive autocorrelation, and then the second test says that there is no negative autocorrelation, then we can say that there is positive autocorrelation. So either test should be able to reject for us to say that that is the kind of autocorrelation present in the residuals. Next, if both tests say that we should not reject the null hypothesis, meaning there is no positive autocorrelation and there is no negative autocorrelation, then it means that we do not reject the null hypothesis as well, meaning the residuals are neither positively nor negatively autocorrelated. Finally, if either test is inconclusive, meaning any of these two tests results to inconclusive results or interpretations, then it means that the overall test is inconclusive. So if the first one is inconclusive and the other one is do not reject the null hypothesis, then it means that we cannot say if the residuals are autocorrelated or not. In this section, I will discuss other computations and other analysis that can be done through linear regression. So in regression analysis, we also have the mean square error and the standard error. So to compute for these, we have the following formulas. So the sum of squared errors, or SSE, is computed using this formula. So that's simply the summation of the squares of the residuals or the summation of the square of the difference between each value of y, the observed value of y, and the predicted value of y. Now, the mean square error, or denoted by s squared, or MSE, is equal to SSE over n minus 2. And this is a point estimate of the residual variance, while the standard error S is the square root of the mean square error. And this is the point estimate of the residual standard deviation sigma. Now, we can a regression model is not likely to be useful unless we can say that the relationship between x and y is statistically significant. And in order to test the statistical significance of the relationship, we focus on testing the significance of the slope. And in this test, we use the null hypothesis, beta sub 1 equal to 0, where and the alternative hypothesis states that b sub 1 is not equal to 0. Now, why do we focus on the slope when testing the significance of the relationship? Because we know that if the slope of a line is equal to 0, it means that the line is horizontal, is parallel to the x-axis, which denotes that regardless of the change in the value of x, it does not change, or there is no corresponding change in the value of y. So y is constant, whatever the value of x is. So that indicates that there is no relationship between x and y. So as long as we can show that the slope of the regression model is not equal to 0, then that is enough for us to say that there is a statistically significant relationship between x and y. Now, to perform the test, we have these guides. So the test statistic is computed using this formula. That's b sub 1 over s sub b sub 1, where s sub b sub 1 is equal to s, or the standard error, over the square root of SSXX. So in order to perform this test, the assumptions of the regression should also be satisfied. And here are the rules in making in interpreting the results of the test. So you have a critical value rule and you have the p-value method. So again, as long as the test statistic is greater than the critical value, or if the p-value is less than alpha, then we can say that we can reject the null hypothesis and we can say that the slope is statistically significant. Here, the values for t are based on n minus 2 degrees of freedom. So degrees of freedom now for simple linear regression is n minus 2. Now, we can also perform an overall f-test for the significance of the relationship between x and y. So the f-test statistic is computed using this formula. That's the explained variation over the unexplained variation divided by n minus 2. Here in this test, the null and the alternative hypotheses are similar to the hypotheses in the previous slides. And the rejection rules are the same. If the test statistic is greater than the critical value, or if the p-value is less than alpha, then we can reject the null hypothesis and conclude that there is a statistically significant relationship between x and y. And here, since we are using an f-test, the f-table will be used as the basis for determining the critical values and the p-values. And the f-score should be based on numerator degrees of freedom of 1 and denominator degrees of freedom of n minus 2. So here's an illustration of the rejection rule. So again, the critical value depends on the f-score that gives you an area of alpha to its right, with a numerator degrees of freedom of 1 and a denominator degrees of freedom of n minus 2. Or you can just check the p-value if it's less than alpha, and that is enough for us to make a conclusion about the relationship between x and y. Now, aside from those two tests, we can also test for the significance of the y-intercept. And in order to test the significance of the y-intercept, we have these formulas. So the test statistic is b sub 0 over s sub b sub 0, where s sub b sub 0 is equal to s times the square root of 1 over n plus x bar squared over ss xx. Now, the rejection rules are very similar to the rejection rules for testing the significance of the slope, where the t-scores and the p-values are based on n minus 2 degrees of freedom. Now, you can also compute for the confidence interval for the possible value for beta sub 0, and that is computed using this formula. So any of these two methods can be used to test the statistical significance of the y-intercept. Now, linear regression or regression analysis also allows us to determine how useful a particular regression model is. And that is denoted or described using a measure called the simple coefficient of determination. And this is denoted by the symbol r squared. So that is the simple coefficient of determination. Now, the simple coefficient of determination is based on the concept of variation. So here are some formulas that will allow us to compute for the simple coefficient of determination. So we have the total variance. That's a summation of the squared differences between each observed value of y and the average. Explained variation is also another summation of the square deviation of each predicted value of y from the average. And unexplained variation is the summation of the square deviations of each value of y, the observed value of y, and the predicted value of y. Now, the total variation is the sum of the explained and the unexplained variation. And in order to compute for the simple coefficient of determination, we just have to divide the explained variation by the total variation. So that tells us that r squared is a measure of the proportion of the variation that is explained, or the proportion of the explained variation to the total variation of the model. Now, once we have the simple coefficient of determination, we can also compute for another measure called the simple correlation coefficient. And this is denoted by small letter r. Now, this is equivalent to the Pearson's correlation coefficient that was discussed earlier, where the interpretation is based on the sign, and the sign of r depends on the value of the slope. So if the slope of the regression model is positive, then r will also be positive, while if the slope of the regression equation is negative, then r is also negative. So we look at the slope of the line in order to determine the sign of R. And the simple correlation coefficient, since it's similar to the Pearson's correlation coefficient, is a measure of the strength of the linear relationship between x and y. Now, here are some graphs that show us how the plots or the scatter plot will look like based on the value of R. So here in this graph, we can see a perfect positive correlation because this data set has an R of 1. This shows a positive correlation or a positive R, and that is seen by the increasing trend of the lines. Here we have little correlation, so R is expected to be near or close to 0 because there seems to be no linear relationship between x and y. Here, this scatter plot indicates a negative correlation, so the trend of the line is decreasing, and this line here shows us a perfect negative correlation. So there is a perfectly straight decreasing line indicating a negative relationship between x and y. Now we can also test the statistical significance of the population correlation coefficient. Remember, we only have the simple correlation coefficient, and this is only based on a sample. And in order to test if the simple correlation coefficient indicates a statistically significant correlation, then we can perform this test. So in the test, the null hypothesis states that rho is equal to 0, and the alternative hypothesis states that rho is not equal to 0. So the test statistic is given by this formula, that's R times the square root of n minus 2 over the square root of 1 minus r squared. So this test will give the same results as the test for the significance of the slope coefficient b sub 1. But again, it's just another way for us to test if there is really a statistically significant relationship between x and y. Let's have the QHIC case, an example for the regression analysis. So QHIC or Quality Home Improvement Center operates 5 stores, and we wish to study the relationship between home value and the yearly expenditure on the home upkeep. So this dataset was obtained for that particular study, so it shows us 40 pairs of values of x and y, where x is the value of the home in thousands of dollars and y is the upkeep expenditure in dollars. So in order to perform the test, again, we have to validate the assumptions first, because if the assumptions are violated, then it might not be appropriate for us to make inferences about the population of x and y. So here, the random sample of 40 homeowners gives us this scatter plot. So the scatter plot seems to be increasing, so there seems to be a positive relationship between x and y. And computing for the intercept and the slope, that's the intercept, that's b sub 0, and then the slope here is b sub 1, will give us these values. So the intercept is negative 348.3921, while the slope is positive 7.2583. And again, that's consistent with the trend of the line that we have observed in the scatter plot. Now, to verify the assumptions, let's look at these graphs. So we have here a stem and leaf display of the residual. So this is an output from the statistical software Minitab. So we can see that there seems to be a bell shape, a proximity bell-shaped symmetrical curve for the residuals. So it is suggesting that the normality assumption is satisfied. Now, using the normal probability plot, So this is something that you can produce using Megastat, Minitab, or SPSS, or even just Microsoft Excel. So it shows us the plot, normal probability plot, and as we can see here in these two plots, it seems to be a straight line. So again, it's not a perfect straight line, but it's approximately a straight line. So this is good enough for us to say that the normality assumption is satisfied. Now for the constant variance assumption, we have here two residual plots. We have here the residuals versus the fitted values. So this refers to the residual between the predicted value and residuals. And here we have the residual plot for the independent variable and the residuals. And as we can see in the two residual plots, we have uh, uh, plots that are normally that seem to be randomly dispersed, so we don't see a funneling in or a fanning out trend for the two residual plots. They seem to be relatively horizontal, so this is enough for us to say that the constant variance assumption is satisfied. Now, since these graphs indicate that the assumptions are satisfied, then we can now proceed to interpreting the regression results using statistical software. So this is an example of the results of the regression analysis using statistical software. Now, these values are all computed using the formulas that were discussed earlier. So first, we have a regression analysis table. So it shows us the values for R square, or the simple coefficient of determination. We also have R, or the simple correlation coefficient. We also have the value for S, or the standard error. Now, we also have another table for ANOVA. So we have SS for regression, residual, and total. Here, this value is actually just your uh, 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 as shown here in the legends, that's the explained variation. So this is something that you can use to compute for R squared, while 11 is the unexplained variation and 12 is the total variation. So to compute for R squared, we can just get the ratio of this 10 and 12, and you will also get the R square of 0.889. Now we have here the degrees of freedom, and we also have the MS values. So the ANOVA table also shows us the value for F, which is computed using the formula presented earlier. And at the same time, it also provides us the p-value, or the area to the right of this F score. And here, that's 9.49 times 10 to the negative 20, meaning the p-value is very small. It's very close to 0. And here we can conclude that the the overall relationship between x and y is statistically significant. Next, we can look at other regression results. We have here a row for the intercept and a row for the value. So the intercept indicates the coefficient and some computations for the y-intercept. And the next row is for the coefficients and the computations for the independent variable. And for this case, that's the value of the whole. So the coefficients are shown here. So the y-intercept is negative 348.3921, which is again what we computed earlier, what was shown earlier. And 7.2583 is the slope. And again here, that is positive. Now, these are the standard errors for the intercepts, and these are the test statistics. Now, the statistical software also provides us the p-value. So in order to make interpretations, then we simply just have to look at the p-values. And both p-values are extremely low or extremely small. So we can say that the intercept and the slope are both statistically significant. Now, if you look closely, the p-value for the f-test is the same as the p-value for the t-test for the slope. So they will always be equal for simple linear regression. And again, both are used in order to interpret if there is a statistically significant relationship between x and y. Now, this particular regression results also show us predicted values for a specific value of x. So if x is equal to 220, then the model was able to make a prediction for y, which is 1248.42597. In regression analysis, we can also compute for intervals. Particularly, we have confidence and prediction intervals. Now, the point on the regression line corresponding to a particular value of x sub 0 of the independent variable x is y hat equal to b sub 0 plus b sub 1 times that x sub 0. Now, it is unlikely that this value will equal the mean value of y when x equals x sub 0 because, again, there might be other factors that can affect the value for y. So there is a normally distributed error term. So the value for y will not always be equal to the average that is estimated using the regression equation. Therefore, we need to place bounds on how far the predicted value might be from the actual or observed value from the sample. So first, we have the confidence interval for the mean value of y. So we can construct a 100 times 1 minus alpha % confidence interval for the average of y when x is equal to a particular value. So using this formula, we can estimate the range of possible values for the average of y when x is equal to a certain value x sub 0. So that is y hat plus minus t sub alpha over 2 times s, or the standard error, times the square root of 1 over n plus the quantity x sub 0 minus x bar squared over ss xx. And here the t-score, alpha over 2, is based on n minus 2 degrees of freedom. So for the QHIC case, the confidence interval was also provided. That's 1187.78944 to 1309.06251. And these two values were computed using that formula. So here, if you have a certain value for x, which is 220, so that will be your x sub 0. Now, y hat, the predicted value using the model is 1248.42597. So that will be the value of y hat in this formula. Now, the t-score can be obtained from the t-table. So here, the dataset is from a sample of 40. So degrees of freedom will be 38. So the corresponding t-score with degrees of freedom of 38 and an alpha of 5%, this is a 95% confidence interval, will give us a t-score of 2.024. Now the s here can be determined using the formula shown earlier, or that is the standard error shown here. That's 146.897. Now n again is just 40. X bar is the average of all the values of x. So if you go back to your dataset, the average of the 40 values of x is equal to 174.4885. And then finally, SSXX is computed earlier in order to compute for the slope. And SSXX again is 124,951.798. So plugging in all those values to the formula, you will get this confidence interval. Now, The next interval is called the prediction interval for an individual value of y. So if the confidence interval estimates the value for the average value of y when x is equal to a particular value of x, the prediction interval provides us a range of possible values for the individual value of y, or the actual value of y given a certain value of x. So we are not estimating an average for y, but the actual value for y. And that is computed using this formula. Now, it's very similar to the formula for the confidence interval for the mean value of y. It's just that this one adds plus 1 inside the square root. So the t-score is also based on n minus 2 degrees of freedom. So plugging in those values to this new formula will give us this interval, this prediction interval with the lower limit of 944.92879 and an upper limit of 1551.92315. So again, how do we interpret these intervals? If your value for x is equal to 220, the average value for y is somewhere between this interval. At the same time, if the value of x is equal to 220, the value of an individual y can be between 944.92879 to 1551.92315. So again, the prediction interval is useful if you want to predict the individual value of the dependent variable y. While a confidence interval is useful if you want to estimate the value for the average of y. So the prediction interval will always be wider than the confidence interval because again, we are interpreting for an exact value instead of an average, and mathematically that's because we are adding 1 to the formula.